Hello, in this video we are going to see how we can get information about the solutions of some type of differential equations without really solving them. And this is going to be done using what is called slope fields and isoclines. We are going to assume that our differential equation has a special form. It's going to be a first order differential equation, and we should be able to write it as, let's say, the derivative of y with respect to x is equal to a function of x and y. In this case, each time we have a point x0, y0, we can find what will be the value of the derivative of the function y at that point. So we don't know what the function y is. That's unknown in our differential equation. But at each point x0, y0, we can find the value of the derivative at that point, because that's given by evaluating the function f at x0, y0. The slope field is a set of all the tangents at all the points. And if we know the tangents of the curves, we are going to see how we can get an idea of how the function looks like, even if we do not know the function. I also mentioned isoclines, and an isocline is a set of all the points at which the tangents to the solution curve have the same gradient. Consider the following example. Let's say the differential equation is dy dx is equal to 2y plus 1. We want to, first of all, sketch the slope field by hand. Then we want to use the calculator to check it. And we want to include the isoclines for, let's say, k equals 0, 1, and 2. So let's see how this is going to look like. Let's draw a set of axes over here, and it's going to be a matter of organizing information. So we want to see, for some points on the space, so these are the points x, y, we want to see what are the derivatives of the function y, solution of the differential equation at those points. So let's make a table over here. Let's look at different possible values for the derivative, and let's look at what will be then the values for y. You notice that the function we have here, the f from the general form, is 2y plus 1, so it's just a function of y and it does not depend on x, and that's why we are writing just y over here in the second column of our table. So let's say, for instance, we look at when the derivative takes the value 0. So that means when the solution is going to have tangent with slope 0, so horizontal. So what we want then is 2y plus 1 to be equal to 0. And this happens exactly with y is equal to negative a half. So it doesn't depend on the value of x, it just depends on the value of y. Let's draw over here. All these points over here are in the line y equals negative 1/2, and in all these points we are going to have derivative 0 for the solution of our differential equation. For the point 1, we need 2y plus 1 to be equal to 1, so that means that we need y to be equal to 0. Let's check 2 as well. If we need 2y plus 1 to be equal to 2, this is going to be true when 2y is equal to 1. So we need y to be equal to a half. Let's add these lines to the picture. So the line y equals 0 is the x-axis, and then we also need the line, which is a different color, the line y equals a half. And let's add one more value. Let's add the value -1. We need 2y plus 1 to be equal to -1. So that means that we need 2y to be equal to -2. So we need y to be equal to -1. So let me add one more line over here. That will be the line y equals -1. Okay, so what do we know? We know that if we consider a point that lives on the line y equals -1/2, then the slope is going to be 0 at that point. And that's going to mean that the solution is actually going to be the line y equals -1/2 itself. Let's write a note over here. We are going to check that that's in fact the solution. Y equals -1/2 is solution to our differential equation. Now we can see that y equals 0 corresponds to slope 1. So anytime we cross this line, we are going to have a slope of 1. So I'm going to draw small lines with slope 1 in all of them. And if we cross the line y equals a half, actually the slope is going to be a bit more. It's going to be 2. So I'm going to draw small lines like this. Also, we have a slope -1 at the line y equals -1. So it's going to look like something like this. And we can see what the pattern will be if I consider horizontal lines y equals k, with k increasing, the slope will be increasing, and with k decreasing, the slope will be decreasing. So now I'm going to take another color and I'm going to use that information to sketch how a solution is going to look like. So for instance, the solution comes from here, it's going to be almost horizontal, and it's going to go to slope 1, it's going to keep going to slope 2, and then it's going to cross slope 3, and so on. And it's going to look like this. And so I'll say solutions will look like something like this. So we have some information about the solutions even if we did not find them. Also, we have a symmetric situation on the other side of the line y equals -1/2. It's going to look like something like this, where the lines get more and more steep with negative slope. So we sketch the slope field. The slope field doesn't need to include the solutions. I can delete them so we can see the small lines showing what the tangent is at each point. Yeah, and we also did what are the isoclines for different values. So for instance, all the points that have tangent 0 are in the line y equals -1/2. All the points that have slope 1 are in the line y equals 0, and all the ones that have slope 2 are in the line y equals 1/2. So this is isocline for 0, for 1, and for 2. And that was part C for this problem. The last thing we need to check is how to do this with a calculator. I have a graph page over here. I'm going to go to menu, to graph entry, and I'm going to select differential equation. And I'm going to write here what my differential equation is. We have here, it's already written y1 prime, so that will be my dy dx. And what I want this to be is 2 times y1 plus 1. And I'm not going to add an initial condition, so we are not adding some value for x0, y1 of 0. So let's see what happens. Yeah, and this certainly looks like the slope field that we did by hand. We had a little note over here that we have to check that the line y was negative 1/2 is actually a solution. And so we need to check that when we do 2 times negative 1/2 plus 1, we get the same as if we take the derivative of that function. But well, on the left-hand side we have 0, and on the right-hand side the derivative of a constant is 0 as well. So it is in fact the solution. Also, I'm going to sketch again here the y-axis that got erased by mistake.